take a look at 8.5 part 2. So last thing we did in part 1 is we represented a vector with two numbers like that. Each one of those numbers means something. It's not a coordinate because there's not parentheses around it. Okay, there's those angle brackets, and those brackets tell you that this is a vector. Does anyone remember from yesterday, what is the 2? These are both components, but one of them is the something component, and the other one is the other component. Yep.
2 is the horizontal.
This is the horizontal. And the 3? Yep. That's your vertical. So the idea is if you wanted to draw that vector, well, you need a piece of graph paper. And that there. Now this doesn't tell you where to start. You can start anywhere you want. So pick a place to start. And it says from that you go 2 units right and 3 units up. So 2, 3, and that is a picture of the vector 2, 3. Now you can start anywhere. You can start over here. 2, 3. And you can start over here. 2, 3. Those are all the vector 2, 3. You put it wherever you want. Any question on that? Now, even though these vectors are all in different spots, okay, this is called the initial point, that's called the terminal point. All of those vectors have different initial and terminal points because they're in different spots, but they are all the same vector. Okay, so that's the first thing I want to start out with. It doesn't matter where you draw it. If the horizontal components of a vector match and the vertical components match, then they are the same vector, even if you draw them in different spots. So every one of these vectors goes 2 right and 3 up. They all have a horizontal component of 2 and a vertical component of 3. When those components match each other, they are the same vector. Okay, so I just want you to understand, placement doesn't matter. It's not where you put it. It's how many right and how many up. Or if these numbers were negative, it could be left and down. Okay, so any question on why every one of these vectors are equal to each other? All right, so this was one notation we looked at, actually drawing it as an arrow. This was the second notation we looked at, using angle brackets and putting 2 numbers inside the brackets. And today we're going to look at a third notation, and that's the one that we're pretty much going to stick with for the rest of the week. And this notation is called unit vector notation. Now, yesterday we talked about the word unit, and we've also mentioned the word unit when we did unit circle. When we talked about a unit circle, does anybody remember how big of a circle was that? If it was a unit circle, yep.
1 unit.
1 unit, yep, had a radius of 1. So when we talk about unit vectors, those are vectors with a length of 1. I think I mentioned it yesterday, but there are certain letters that you do not want to use when you name a vector. Okay. We use letters. Maybe I should mention one other thing about the letters. If you just write a letter, it could be a variable. How do we make sure when we write a vector that somebody knows it's not a variable and it's a vector? Yep.
Put an arrow on top of it.
You can put an arrow on top of it. So if you want to talk about vector x, you could do that. Or there's one other way you can make the letter look different so we know it's not a variable. Yep.
You can make it bold.
You can make it bold. So So those are the two ways that you can use letters to name vectors. And we won't confuse them with variables. Now, generally you can pick any letter you want to name a vector, except there's 3 letters you can't use, I, J, and K, because those are special. Right? So I'm going to show you what some of those are right now. So you're talking about vectors, and you use the letter I. Okay, nothing to do with imaginary, so don't think imaginary at all. Vector I is automatically a vector that points to the right, and it is 1 unit long. It's a vector that kind of has a special name. Everybody knows the vector I points to the right, and it's 1 unit long. It's kind of like the letter pi in math. Okay. At this point, everybody knows pi means 3.14. It's a special symbol for that number. Well, this is a special symbol for this vector. That's a picture of the vector I. It's 1 unit long, and it points to the right. Okay. The other special vector that we're going to use a name for is J. And the vector J is 1 unit long, and it points up. Now I mentioned K. K I'm not going to put up there right now. K is if we were doing 3D. So I is the one that points like left and right. J is up and down. K would be like in and out of the board. Okay, that'd be like a 3D. For now, we're just going to stick with I and J. What's another letter you might not want to use for a vector? Not because it has a special name. It's just it might be confused because it looks like something else. Yep.
O.
Yeah, I would use the letter O as a name for a vector because it might look like a 0. So, what is this unit vector notation? How do we use I's and J's? What is that? Well, I'm going to show you basically how we can use the I and J and stack them together to build a vector. So you're going to think of I and J as like Lego pieces, like building blocks. We're going to stack them up to build a vector. Alright, so let's see if we can build the vector 3, 4. Now, it doesn't matter where I start. I'm just going to start right there. How do I get to where this vector is going to end based on the 3 and the 4? Yeah?
You'd have to go right 3 times, then up 4 times.
Right 3, up 4. So there is a picture of the vector 3, 4. Now, how can I build that with I's and J's? Yeah?
3 I's, 3 J's.
Yeah. So what I'm going to do is stack the I's and J's together till I get from where I started to where I stopped. Well, first I need to move right 3. So that means this is I, this is J. I'm going to stack 3 of the I's together first. So there's an I, there's an I, and there's an I. So that's, how many I's did I just use? Yeah, 3. So I did 3 of the I's, plus, now I need to stack some more on the end of that till I get up to where I'm going to stop. How many do I need? Well, there's 1 J, there's 2 of the J's, 3 of the J's, and 4 of the J's. So if I stack 3 I's together and 4 J's together, that's how I can build this vector out of I's and J's. 3I, 4J. Yeah?
Where did you get the red vector from? Was that there at the beginning of the problem?
Yep, that was given to me. Yep. So that they gave me the red vector. Now, i's move you right, j's move you up. But what if you had a vector like this? I don't need to move right. I need to move up, but I need to move left instead. So what do you think I'm going to have to do to move left instead of right? Yeah?
Use the opposite side of your eye.
Yeah, use negative I. So in this case, I need 1. I need 1 more. 2. So how many i's did I just use right there? Yeah?
-2.
Right. That's -2 I. And then I have 1, 2, 3, 4 of the j's. So there's another example of how you can build this vector out of i's and j's. So by making I positive or negative, you can go left and right. And by making j positive and negative, you can go up and down. So you can move in any direction you want. And you can use half of an I or a quarter of an I. You know, if you want to go in between 2 grid lines, you can do that. So that's basically all there is to writing a vector with ij notation. It's pretty similar to the notation we had yesterday, except you take out the brackets, take out the comma, and put an I and a j next to the 3 and the 4. It's pretty much it. Okay. How about if I had one like this? Let's do this one. Right. How would I write that vector using i's and j's? You have to put the I first and then the j second, alphabetically. Yeah?
2i.
Yep, so 2 of the i's.
Minus 4j.
And then we have 1, 2, 3, 4 j's going down. That makes the j's negative. So it's 2i minus 4j. So rather than writing vectors, or rather than drawing vectors, we're going to write them like this now, using the i's and the j's. Because if we write it like that, then we can start doing a lot of the things we did yesterday without sketching. We're just going to use numbers today. Question on that one? Okay. So let's look at some formulas that we did a little bit yesterday visually, and now we're going to do it today with all numbers. In these formulas, I need to write a few things. Anywhere you see a V and a W, those are vectors. I know they don't look bold, but if you're not sure if something's bold, just ask me. And alpha is going to represent a scalar. What did we say yesterday that a scalar can do to a vector? It can do one of 3 things. Yeah?
Does it make it longer, shorter, or reverse it or change the direction?
Yeah, exactly. So a scalar, think of when you scale, make a scale model of like a house. It's a small version. If you make a scale model of a cell in science, you probably make a big version. So scaling means to make it smaller, bigger, or it can also flip the direction. Okay, so here's the 2 vectors I'm going to work with. When we start doing an actual problem, those 2 vectors are going to have all numbers like this. Okay, but for now, vector v has a horizontal and vertical component, and so does vector w. Now, when we talked about adding vectors yesterday, this is how you had to do it. If that's a vector, and that's a vector. So you want to add those 2 together visually. I explained this in the video, but you have to line them up like that. And then you have to draw the diagonal. That is what those 2 vectors look like added together. But now we're going to get away from doing that sketch. We're just going to do it with numbers. All you have to do when you add vectors as numbers is think about like combining like terms. You can add the x components together, and then you add the y components together. And that's it. So there's no sketch. Subtraction is pretty much the same idea. You subtract the x components and subtract the y components. With subtraction, the order is important. If you switch the order you subtract in, you do not get the same answer. Think of 5 minus 2, and then think of 2 minus 5. So follow the order they give you. Okay, so it's adding and subtracting. And this is scaling. So when we scale a vector, we don't use 2. When you add, you need 2. When you subtract, you need 2. But when you scale, you only need 1. And the way scaling works is you might have a number like that, 3b. That would take the place of alpha. This 3 is basically like a distributive property. This means to triple the length of vector b. So how do you triple the length? Well, you multiply the x component by how much you want to increase it by, and then you multiply the y component by what you're increasing it by. So if you wanted to triple a vector, you'd multiply each number in the vector by 3. But you have to do each number, not just one of the numbers. Okay, we're going to go through an example of each one. And then this symbol, the double bars around a vector, what does that mean? Yeah?
Is that absolute value?
So it, well, not quite. Yeah.
That would be the magnitude of vector.
It's the magnitude. So what it shares with absolute value is it is always a positive answer. But the magnitude means, what is that? Can you describe what magnitude means?
It's
Like,
kind of like the like if you have a line, it's the distance between the 2 points.
yeah. So it's the length of the vector. Well, let's look at this red one right here. The way I drew it, it pretty much spells it out for you how to find it. How do you think you would find the length of that vector in red? Yeah? Yeah. You take the horizontal component, which we call x, and you square it. You take the vertical component, which we call y, and you square it. You add them together and you take the square root. So x squared plus y squared equals the length of your vector squared. So it is the Pythagorean theorem. And there's the formula. X component squared plus the y component squared, and you take the square root. And as I mentioned earlier, always get a positive answer out of that, because distance can't be negative.
Can you go back up to the first one?
So what we'll do, we'll try an example of each one of these. So here's the 2 vectors that we're going to work with. I've written them in both notations we learned, the one we did yesterday and the one we just learned today. We'll practice both. Now, a lot of what we're going to do in this problem we did yesterday. But when we did it yesterday, we drew it. Today, no drawing. All numbers. Okay, so the first thing I want to do is add those 2 vectors together. Let's write the answer with i's and j's first, and then we'll write it the other way. Okay. if I add v and w together, what would I get for my horizontal component? Yep. You'd have 5 of the i's. And what would I get for my vertical component? Yep.
Negative j.
Negative j. You could put negative 1j, or you could just put negative j. So if you're going to draw that, that means wherever you start from, you're going to go right 5 and down 1 and draw your arrow. Now, what would that be the same as if you wrote it with the angle brackets? Yep.
5, 1.
5, comma. Yep. Negative 1. Yep. So because that j is a negative, we got to make sure we put the negative as well. If both answers are correct, it's just a matter of which one they would ask you for. Okay, that's v plus w. Let's try v minus w. Okay, I'm not going to be able to keep the originals on the screen because it's going to get too far up. Okay, what's my, let's do it in ij notation first. Okay, unit vector. What's my horizontal component? Yeah.
Negative I.
So we're going to have 2i minus 3i. That's negative I. And what about my vertical component when I do v minus w? Just be careful. Yep. 7j. It's 3 minus minus 4. Yep. So 7j. There you go. Okay. And Eli, if I wrote that with angle brackets, how would that look?
It would be -1. Oh, and then 7.
And then 7. So -1, 7. Any question on that one? All right, let's try scaling a vector. This time we're not using w, just v. And I want to triple the length of v. Okay, so if I triple v, what's going to be my new horizontal component? Yeah.
6i plus
Six.
9j.
So 6i is the horizontal, and 9j is the vertical. So 6i plus 9j. It's like a distributive property to each number. 6i plus 9j. And if you wrote that with the angle bracket, a 6i. Now, let's look at all these answers so far. This is a vector. That's a vector. That's a vector. The answer to this question is not a vector. The answer to this question is a length, which is a single number. And what formula did you just say you basically use when you're finding the length of a vector? Yeah. Pythagorean theorem. Let's go back and look at it. Take the x component, square it. Take the y component, square it. Add them together and take the square root. And we are doing this for v. So you do not need w. Okay. What's the, when I say x component, I mean horizontal. What's the horizontal component of v? Yep, 2. And I'm going to square it. What's the vertical component of v? 3. I'm going to square it. So I have to square them, add them up. I got to do one more thing. Yeah.
Take the square root.
Take the square root. So these are two sides of a triangle, and you're using the Pythagorean theorem to get the hypotenuse. And what's that going to give me? Square root of? Yeah, 13. So you can leave it just like that. If they want a decimal, you just type it in and get your decimal. So that's how you add, subtract, scale, and find the magnitude of vectors with no sketching at all. Any questions on those? Okay, so a little bit of a review from yesterday. We talked about if you have a vector that is a length of 1, and I kind of mentioned this today already, that's called a unit vector. What I want to look at is what happens if we have a vector that's not a unit vector, and we want to make it a unit vector. Well, if it's too long, we may have to shorten it. If it's too short, you may have to lengthen it. But the goal is going to be to somehow get a vector that always has a length of 1. So let's look at a couple examples and see if you guys see a pattern. Let's say I had a vector that has a certain length. And then what I would have to scale that vector by, to make let's say make it equal to 1 unit. Let's say I had a vector that was 5 units long. What would you scale the vector that's 5 units long by to shrink it down to 1 unit? Yeah? 1/5. What if I had a vector that was 3 units long? What would you scale it by to make it 1 unit? Yeah? 1/3. What if I had a vector that was 1/4 of a unit? What would I scale that by to make it 1 unit? Yeah? 4. So if you look at the first 3, you might see a pattern with the number on the left and how you get the number on the right. So now I want to extend that pattern to, let's say, x units. If I had a vector that was x units long, what would I scale it by to make sure that it was 1 unit? Yeah? 1. Well, what if x was like 5 though? You couldn't scale it by 1.
Oh, but we don't know.
Yeah?
1/x.
1/x. If you scale something by its reciprocal, okay? 5, 1/5. 3, 1/3. 1/4, 4/1. If you scale something by the reciprocal of its length, it will force it to always be 1 unit long. That's the pattern. So let's write that down. So how do you find a unit vector if you're just given some random vector? Well, you either have to make it longer or you have to make it shorter to make sure it's 1 unit. So when we do this, we're finding a new vector that still points in the same direction. Nothing's changing about which way it points. All we're doing is making it longer or shorter to make sure that it's exactly 1 unit. So let's say I have that vector v. What do I have to scale that by to make sure that it is 1 unit long? Yep.
1/v.
And when you say 1/v, 1 over the what of v? Yeah? The magnitude. So we have to scale it by 1 over its length. So if its length was 5, it'd be 1 over 5. If it was 2, it'd be 1 over 2. And remember, when you multiply a vector by a scale factor, how do you do it? It's like a distributive property. You multiply each component by whatever you're scaling by. So if I simplify what I just wrote right here, you could multiply these together. Think of that as like a fraction v over 1, and multiply straight across. V times 1 is v, and 1 times the magnitude is just the magnitude. So that's the formula for finding a unit vector. Take the vector and scale it by 1 over its magnitude, or divide it by its magnitude. That means the same thing. I think of it more usually like this, but what's in the box is the same thing. Let's try an example. So it says to find the unit vector for 3i minus 4j. Well, first thing we got to figure out is that already a unit vector? If it is, then we're done. If it's not, then we'll fix it. How do I find the magnitude of v? Yeah. Okay. Can you give me the formula for it?
3 squared. Well, would it be minus 4 squared or plus 4 plus negative 4 squared, or does the negative not apply?
Well, how would you do it in Pythagorean theorem? It's the same.
Well, if it's squared, it's even. But it'd be
You mean positive?
positive, yeah.
Yeah.
If it's squared, it's positive. So how would you write it?
So whether you put the negative or not, it doesn't really matter because it is going to cancel out.
Okay.
So you can put it however you want.
All right. 3 squared plus 4 squared equals. All right, and then take the root of that.
Yep.
Equals the magnitude.
And so what's the magnitude of this vector? Yeah. 5. So that answers the question if it's a unit vector or not. Is that a unit vector? No. It's 5 times too big. So what are we going to scale that vector by to shrink it down and make it a unit vector? Yep. 1/5. So we're going to take the vector and we're going to divide it by 5. Or it's multiply by 1/5. That's the same thing. So we're going to do 1/5 of vector v. And that's going to shrink it down 5 times as much. It's going to make it a unit vector. So if that's v, 3i minus 4j, what would 1/5 v come out to? Yeah? 3/5 5. That's when you multiply the first part by 1/5. Yep, and the second part? Negative 4/5. Okay. So that's a vector that points exactly the same way as the original one. All we did was make it 5 times smaller. That's it. Any question on that? Now, what if I had something like this? Let's say 2i plus 3j plus 4k. We called that vector W. That's not a two-dimensional vector. That's three-dimensional. The way I know it's three-dimensional is it has this k part. I and j make it 2D. The k part makes it 3D. How do you think you would find 1/2 W? We talked about how to do it if it was just 2D. But anyone think they'd know how to do it for 3D? Yep.
We should just distribute it out the same, right?
You still distribute it out exactly the same way. You just have to do it one more time. So what do you think 1/2 W would be?
So it would just be I plus 2 over 2J.
And he'd stop right there if it was 2D. That'd be the whole problem. But now just go one more time.
Plus 2J.
Plus 2k. So when we work with vectors in 3D, it's really not that much harder than 2D. You just have to do the same thing you've always done, but one more time. All right, and let's say we had something, let's make up another one. 4i plus j minus k. Now, let's say I wanted you to add these two vectors together. Well, you know how to do it for 2D. Doing it in 3D is pretty much the same thing. When you add them up, anybody think you could tell me what you'd get for the I, the j, and the k component? Yep.
You get 6i plus 4j.
And that would be where he'd stop if it was 2D. We'd be done. But now we just got to go that one more step.
It would be plus 3k.
Plus 3k. So adding, subtracting, scaling, and even finding the magnitude is exactly the same way you do it in 2D. You just have to extend it that one more step to do 3D. We're not going to spend a whole day on 3D. I just wanted to bring that up for those two pretty straightforward cases. So any questions on that? Let's take a look at the last thing. We talked about two two main things we can use vectors for. One of them I showed an example of was like some object moving. In particular, we looked at some airplanes. And if you describe something moving with a vector, that's called a velocity vector. So we're going to look at how we can write the formula for a velocity vector right now. And to show you kind of what the goal is going to be, let me jump to what a problem looks like, and then we'll work backwards and see, well, how would we figure that problem out? So don't write the question yet, because we need to explain what a velocity vector is first. But the idea is you're going to be given two things about an object that you throw. How fast you throw it, and the angle you throw it at. So like a 90-degree angle would be straight up. A 0-degree angle would be perfectly horizontal. 30 is somewhere in the middle. Knowing these two things, we're going to write a vector for this problem. Right, so let's draw it out. So when you throw an object, if you throw it at an angle, it's really traveling in two different directions. Pretend that arrow represents my object. Which way is my object moving? Indicated by that arrow. It's moving, yep. It's moving right and up. So it's going right and up at the same time. Now, I don't know the angle that I'm throwing it at. So let's call the angle what we usually do when we don't know an angle. We use a Greek letter. So we'll call it alpha. And when you write a vector with those angle brackets, if you're doing a two-dimensional vector, how many numbers are inside these brackets? Yep, 2. So you need something here, and you need something here. What does this first number represent? Yep.
The horizontal.
That's the horizontal component. And what does the second number represent? Yep. The vertical. So in order to write a velocity vector, you need to break your problem down into a horizontal component and a vertical component. To do that, I need to make a shape out of this picture. Anybody have an idea of what shape I'm going to make?
Right triangle.
Yep, I'm going to make a right triangle. In red is the horizontal component of the vector. In green is the vertical. We need to figure out what the red and the green components are. The problem is going to give you the hypotenuse. That's not really helpful if you want to write a vector. You need the horizontal and the vertical. So temporarily, we could call this side x, and we could call that side y. What trig function would I use that would involve this side and the hypotenuse? And this is your angle that you're going to be given in the problem.
That'd be cosine.
Would be cosine. So the cosine of my angle equals, it's going to be a fraction. What would go in the top? Yeah. X over. Now we got to be careful because we want to divide by, well, you tell me in general, what goes in the bottom of a fraction when it's equal to cosine? Don't give me anything specific. Just describe what goes in the bottom. Yep. What about the hypotenuse? Like put the word hypotenuse right there?
No, you would put the unit, like the length of the
The
hypotenuse.
length of the hypotenuse. So what is the length of that? How would you write it? Yep. V is the actual image. What do I want to know about the image, though? I want to know the length, and I have a way to write that. Yep.
Or magnitude.
The magnitude, yes. This means specifically the length of the image in black. I don't want the image itself, I want the length of it. Okay. And then how would you get x by itself? Yep.
Multiply both sides by magnitude.
Yeah. Move the magnitude to the other side by multiplying. And that's your formula for the horizontal component of a velocity vector. It's the magnitude times the cosine of the angle. That's the speed you throw it at. That's the angle you throw it at. Now we'll do the same thing for the vertical. Okay, so let me just zoom out a little bit. So we've got our horizontal component. Now we need something to fill in for the vertical. What trig function would use y instead of x? Yep. Yep. So we're going to do sine. Sine of my angle equals opposite over hypotenuse. And we get a little lazy when we say that, but what I really mean to say is the length of the opposite over the length of the hypotenuse. So what goes in the bottom?
the magnitude of E.
Yep, magnitude of E. And now we're going to get y by itself, just like we did with x. So what does y equal?
The magnitude of E, the sine over theta.
Yeah, this really isn't anything new. We've done this kind of thing a lot, where we find the base and the height of a triangle. And that goes right there. So now I'll write that nice and neat, but that's the formula for a velocity vector. Magnitude times cosine of your angle, comma, magnitude, sine of your angle. Formula for velocity vector. There's two ways you can write it. You can write it with the angle brackets, or you can write it with the I and J. If you write it with the angle brackets, it looks like this. Magnitude V, cosine alpha, comma, magnitude V, sine alpha. So that's one way. Or, if you want to do it with the I's and J's, well, just get rid of the angle brackets, take out the comma, put an I after the first one, put a J after the second one. So magnitude V cosine alpha with an I, and then magnitude V sine alpha with a J. Either way, it's the same. But that's the formula for a velocity vector. So again, that's the speed that the object is thrown at. That's the angle that you throw it at. It's the same for the second one as well. Okay, does everybody have that formula? So because it involves sine and cosine and you need to fill in an angle, we do have to usually use a calculator to do that, but that's nothing we haven't done before. I basically just told you all of this. Yeah, that's fine. So here's our problem. It says we're going to throw an object at 50 miles an hour at an angle of 30 degrees. Find the velocity vector. And they tell us they want the answer in unit vector form, which means they want to see I and J. They don't want the brackets. And then we'll talk about what each component means once we get our final answer. That'll be it. There's only two things you really need to know in that whole problem, and I've underlined both of them. As far as the numbers you're going to fill in. Lucas, can you tell me how I'm going to get my horizontal component?
You have to draw the line angle, like the mile per hour.
So we're just going to use a formula. We don't.
Okay.
We already discovered the formula by drawing it, so we don't have to do any more sketching. We just want to use the formula.
The magnitude of 50.
So 50, yep.
Yeah. And cosine of 30.
Cosine 30. And what goes after that, so we know it's the horizontal?
I
Put an I.
plus 50 sine 30.
Sine 30. Yep. Anything else? With a J. Yeah. Okay, so figure out each of those numbers, and that is the velocity vector. We're just going to round things off to 2 decimal places. Anytime I use sine and cosine, what should I always check first? Yeah?
If you're in degree or radians.
Right. I need to be in degrees because the angle they gave me was degrees. I'm in degrees. So that's fine. So 50 cosine 30 and 50 sine 30. So 43.3i plus 25j. That's the velocity vector. The last thing it says is to explain what each of those numbers mean. The 43.3, which component is that? Yeah? Horizontal. And specifically, that's what we call the horizontal speed. So, you're like, wait, why is it horizontal speed? I thought the speed was 50 miles an hour. Yes, it's 50 miles an hour, but that's not how fast it's moving horizontally. If you were standing like in front of this object and somebody threw it at you 50 miles an hour at an angle of 30 degrees, and you pointed a radar gun at the ball coming at you, it would say that the ball is coming at you at 43.3 miles per hour. Because not all the energy went into throwing the ball at you. Some of the energy went into throwing the ball upward. If the person threw the ball at a 0 degree angle, then all of the energy would be moving that ball horizontally. There'd be no vertical at all. So this is the horizontal speed. And what do you think the 25 is? Yeah? The vertical speed. So what would that look like? Well, if you could be in like a helicopter above the situation and point a radar gun straight down at the ball, it would say that the ball is coming up at you at 25 miles an hour the second it leaves your hand. Because of gravity, this number is going to change once it leaves your hand, and it's going to slow down until it hits its peak, and then it's going to start to speed back up again and head back down. Okay, so this vertical speed changes the second it leaves your hand. Horizontal speed doesn't really change. Right? If you think of like the speed when the ball leaves like pitcher's hand, and then the speed that it hits the glove at, the catcher, it's probably the same speed. The only thing that would slow the ball down a little bit would be the air. But because a ball is round and it's such a short distance they're throwing it, probably doesn't slow down that much. And most of the time when a pitcher pitches something, they're probably throwing it at almost a 0 degree angle. I mean, they're not lobbing it in like, maybe if you're in the outfield, you might throw it up a little bit. But if you're pitching it, they're probably pitching it to put all that energy into moving it forward. And that's a velocity vector. Any question on that? All right. So, yeah, that should be good. So it's 25 to 47 odd, and 55 and 57. This is out of a different book, but if you go to Schoology, the PDF that I put for the lesson is the correct PDF. But it's going to look a little different because it's a different book. A reminder, last regular test for the term on Friday. Final will be 2 weeks from Thursday. Tomorrow is going to be a review day for anybody that's not here, so you won't be missing anything. Yes?
Are we going to get some review material before the test? Know what's on it?
This week's test or the final?
The final.
The final, yes, I already made it.
Okay.
It's on Edge Elastic. It's worth 12 points of extra credit.
Oh, we can already go and take it?
I'm going to open it up probably Thursday or Friday. And then you'll have the weekend next week, the weekend, and then the next week.
Awesome. Thank you.